Alright, so this video is going to review some terminology from your first chemistry class about energy and review the Q equals mCp delta T equation. Thermodynamics is what we're going to be focusing on in this part of Unit 2. We're going to focus on this as it relates to both physical and chemical changes. It is the study of how heat changes can occur in these types of interactions as well as work. And we have to look at it from two perspectives, the perspective of the system as well as that of the surroundings. To kind of keep that straight in your head, the universe consists of everything, and the system is what we are actually looking at, the actual change that is taking place, whether it be a physical change or a chemical reaction. The surroundings are anything else that could be affected by that energy change that occurs or interact with the system itself, and together they make up the universe. So if you look at the picture below, basically everything shaded in blue in each of the pictures is referring to the term underneath it. So what's inside the flask is the system. What is surrounding the flask is its surroundings, and then put them together, that makes up the universe. So in this particular example, the chemical reaction is taking place in the solution. We want to focus on the chemical reaction itself. So that is being our system, while the surroundings are anything that the reaction is surrounded by, which would include the water, the temperature, the humidity in the air, anything along those lines, any sort of environmental conditions. But the system itself is the actual reactants that were part of the chemical reaction. So it's something to kind of keep in mind. We can't ever really measure, we can't measure energy changes, period, but we can't even measure the temperature changes of the reactants, but we can measure the temperature changes of the solution in which they're surrounded by. So the law of conservation of energy is very similar to the law of conservation of mass. We cannot destroy energy, we cannot create it, but we can convert it from kinetic to potential, potential to kinetic, thermal to electrical, electrical to chemical. We can convert it to a variety of forms, but the overall energy of the universe stays constant. When energy is transferred as heat, it always moves spontaneously from a warmer object to a cooler object. This is going to play a role in how the heat is going to move between the system and the surroundings. So if you are at a higher temperature, you're going to lose heat and you're going to go through an exothermic change. Your temperature is going to decrease. While if you are a cooler object, you're going to absorb heat, so your temperature is going to increase, and because you are taking in energy, you would go through an endothermic change. An example of this would be hot chocolate, especially during the wintertime. If you take it outside, it tends to get cooler because the heat of the hot chocolate is being lost to the surroundings. It's also why we don't store hot chocolate and coffee in just plastic cups, because it would cool down much more quickly. We want to use good insulators that are going to help to keep the heat within the cup itself. So within exothermic and endothermic, we've talked about those terms before. We have to look at it from two perspectives now, not just the system, but also the surroundings. So when you are going through an exothermic change, let's say wood is caught on fire, the wood is giving off heat as it is being burned. And so since the system is losing heat, it is going through an exothermic change, while the surrounding is taking on that heat. It's becoming warmer, so it is going through an endothermic change. And since we typically measure the temperature of the surroundings, we would see an increase in temperature. While if we are going through an endothermic change, we would see the system take in energy. An endothermic change would be an example of water boiling. When the water boils, it has to absorb energy from whatever heat source you are using to provide that energy source. So because the system is taking in energy, it is going through an endothermic change, while outside of the system, what is giving off the heat is getting cooler, and that would be the surroundings, and they are going through an exothermic change. So you would expect to see the temperature of the surroundings decrease when you have an endothermic change, and the temperature of the surroundings increase in an exothermic change. Specific heat capacity, we're going to refer to it as CP, but you can see it referred to as S and sometimes just as C. It is, we'll review the definition on the next slide, but it's the amount of heat that it's necessary to warm up 1 gram or a mole of a substance by 1 degree, which can be either Celsius or Kelvin. And there are various factors that influence how much heat is being transferred, and the specific heat capacity is kind of representative of those factors. 1 is how much heat is being transferred. 2 is the temperature change, how much temperature change is taking place. And then 3, what is your substance? Some substances are more capable of undergoing temperature changes than others. It's going to be represented in their specific heat values. So here's just a table of them. There's also a table in your textbook. I'll tell you what page they're on. I will do my best to give them to you in your problems. If you have a higher heat capacity, you are more likely to stay at the same temperature for a longer period of time, depending on how much of the substance you have, because you need more energy to warm up your substance as well as to cool it down. If you look, you'll see that water, it has a very high specific heat capacity compared to your metals. If you look at something like sand down here, I know sand's not a metal, I'm just using it as an example. Copper, brass, even aluminum is 0.9. These are substances that warm up quite readily. They also cool down quite readily because they have such small specific heat capacities. They aren't able to withstand changes in temperature as easily, and so they are more effectively warmed and cooled by smaller inputs of energy. So we talked about what specific heat capacity is. Because we are looking at it per degree change or per Kelvin change, it really doesn't matter if our units are in Kelvin or in Celsius, because we're taking the difference between a temperature at one point to a temperature of another. And when you go between Celsius and Kelvin, you're changing by the same amount. You would still have the same net temperature change. Molar heat capacity, as I talked about previously, is the same as specific heat. It's just joules per moles. And where all this kind of comes into play is that because we said according to conservation of energy, we can't lose or destroy energy. The energy absorbed by the system, aka or lost by the surroundings, has to add up to be 0, and vice versa. I didn't have this triangle when I made the video earlier, but I wanted to add it in just to kind of review it with you. Q equals mCp delta T. If you are solving for Q, you would want to multiply mCp and delta T together. If you're solving for M, you would want to divide Q by Cp and delta T. Same thing for Cp, Q over M and delta T. And then finally, with the change in temperature, it'd be Q over mCp. If you don't need that triangle, that's great, but I just wanted to review it with you if it helped previously. So we're going to do a couple of example problems. The first 2 are review. The third one is the only thing that's new in this particular section. And it's just taking the mCp delta T and applying it to both the system and the surroundings. So our first example says it takes 1250 joules of energy to heat a sample of pure gold with this Cp value from 12 to 15.2 degrees Celsius, and we want to calculate the gold's mass. So if this is our equation, Q equals mCp delta T, we're solving for M, and if you go back to the triangle on the previous side, that would be Q over Cp and delta T. So the first thing we're going to want to do is identify our Q, which is our 1250 joules. We're going to divide it by our Cp as well as our delta T. So our Cp is the 0.129. Sorry, the M didn't come up sooner. And then our delta T is the difference between the 2 temperatures, which would be 3.2. Notice again the temperatures in Celsius. The Cp is per unit Kelvin, but because these are both representing changes in temperatures, we can use these to cancel the units out. We don't have to change these over to Kelvin. You can, however, if you wish. The joules cancel, the kelvins cancel along with the Celsius, and that leaves me with 1 over grams, which would be an answer in grams. The temperature change had 2 sig figs, so that's what I want to report my answer as, 3.0 times 10 to the 3rd grams. The second question asked me to find one of the 2 temperatures. It asked me to find the initial temperature of 150 grams of silver, given the Cp value, if 1.8 kilojoules of heat was used to warm the silver to a final temperature of 85 degrees Celsius. So this time I want to solve for delta T, which would be Q over mCp. The reason I'm solving for delta T is because it's a little bit easier to find the initial temperature once I've gone ahead and isolated the delta T by itself. So my Q is in kilojoules, 1.8 kilojoules of heat, while my CP is in joules. So I need to make those units consistent, so I went ahead and changed the 1.8 kilojoules to joules. I divided that by my mass, the 150 grams, and my CP, the 0.24 joules per grams Kelvin. The joules cancels, the grams Kelvin cancel, and that leaves me with Kelvin. I need 2 sig figs, so I got that to be 50 Kelvin. Again, this is a difference, so whether it's 50 Kelvin or 50 degrees Celsius, it makes no difference. Because we measure temperature in Celsius, I went ahead and switched it back to Celsius. I substituted in my final temperature of 85, and so to isolate T initial, I subtracted 85 from both sides and solved for Ti, which would give me 35 degrees Celsius. Alright, so a lot of times when we do problems like this in lab, or when we do experiments with this, we do them in coffee cups. We use styrofoam cups, and we usually put some sort of cover on the top to act as an insulator to try to minimize any heat loss to the surroundings, so that we can measure the temperature changes associated with the solution and use that to figure out information or quantities about the system. And that's what we're going to do in this particular example. This is just a physical change. We're taking 15 grams of nickel, we've heated it to 100 degrees Celsius, and we've added it to 55 grams of water. That was at a different temperature, 23 degrees Celsius. So there's my nickel to start with, and there's my water to start with. We are going to assume when we combine these together that all the heat that the nickel has to lose, because it's the warmer object, to the colder object, the water, would be consistent, that the water would absorb it all, the nickel would lose it, and so we want to know what the final temperature is when they are both at equilibrium. And you're given specific heat values for both metal and both the nickel and the water. So we know that the system's heat that's lost should equal the heat that the surroundings absorbed. And so if we wanted to solve for them in terms of one another, the nickel would be equal to the water's heat, but one would need to be negative since one's losing and one's gaining. We also know how we can find the heat of the nickel, or the Q of the nickel, by solving for MCP delta T, and the same for the Q of the water. And so this is basically the same equation on both sides, it's just specific to the substance that's on that side as well. We know the mass of the nickel, we know the specific heat of the nickel. We do not know the final temperature of the nickel, but we know the initial, and we know the same for the water. Now at this point there are a lot of units running around, and if you want to drop the units, that is fine. You can also take these two sides of the equation, put them in your calculator, graph them, find the intersecting point, which would give you T final. It does not matter to me how you do it, but you would need to at least show me this to this point, what you substituted in, so that I knew what you were solving for. I'm going to go ahead and do the algebra through, and I will include the units just so you can see where they went. I'm going to combine the constants after I cancel out my units of grams. And so I get that 15 times 0.444, negative 15 times 0.444 gives me negative 6.66 joules per Celsius. The T final minus 100 stays put. And I'm going to multiply 55 times 4.18 to give me 230 joules per Celsius. Again, T final minus 23 degrees stays put. I distribute through the constants on both sides, and that gives me what you see there. The negative 6.66 was multiplied through to TF as well as to the 100. When it was multiplied through to the 100, the Celsius canceled. And then the same thing occurred on the right side between 230 joules per Celsius and the 23.0 degrees Celsius. At this point, I combine my like terms. So the joules terms go together, as well as the joules per Celsius TF terms go together. And I isolate TF because that's what I've been trying to find. That's my final temperature. So when I divide both sides by 237, I see that the final temperature should be 25.1 degrees Celsius. So I believe that is the end of the first part of this review, and that should help you with what you need to do in class tomorrow.